Hello students, today's our lecture is focused on mass spectroscopy, especially the fragmentation pattern of some important functional groups. So friends, as you know that there are so many functional groups in organic chemistry. So what we are going to do, we will divide these lectures in two parts. So in today's lecture, we will cover 7 different types of functional groups, and in next video lecture again 7 to 8 functional groups we will discuss. So each and every functional group has a fixed fragmentation pattern which will help us to recognize the fragments which is removed from that molecule. So friends, without wasting time, let's begin with our first functional group, that is a alkanes. As you know that alkanes are saturated hydrocarbons, and most of the time we don't have a lone pair or non-bonding or pi electron in alkane. So alkanes have a specific fragmentation pattern, and their fragmentation pattern is quite predictable because all the fragmentations are stabilized according to the stability of carbocation. So friends, whenever we have alkanes, the fragmentation pattern will be depend on the stability of carbocation. So in this case, the isobutane will fragment over here, and we get this kind of secondary carbocation or radical cation, and which will have the peak at 43, whereas the isobutane have the molecular ion peak at 58. So there are very simple and predictable patterns for alkane. Now you can see here in the second example, that is a butane. Butane doesn't have many substitutions, so it will break in a such a way that it will form a secondary carbocation. Okay, so you can see 12, 24, 36, 37, 38, 39, 40, 41, 42, and 43. So this 43 is corresponding to radical cation of CH2, CH2, and CH3. So this is how the fragmentation pattern of alkenes we can predict by the stability of carbocation. So let's go for the next functional group. Our next functional group is cycloalkanes. Cycloalkanes are just cyclic alkanes, so they are not much different from the alkanes. But as you know that there is a cyclic ring, or there is a ring, so there is a typical fragmentation pattern of losing a ethene molecule. As we discussed in the rules of fragmentation, the fragmentation always proceeds with the loss of small and stable molecules such as ethene. So as if we remove the ethene from this molecule, we again get the loss of 28. So if we reduced 28 from 70, we get again the molecular ion peak at 42. Okay, we get molecular ion peak at the, sorry, base peak at the 42, and molecular ion peak at 70. So this 42 is formed by loss of ethene molecule. Similarly, in the next example of bicyclic Norbornene system, if we remove the ethidine or ethene from our molecule, we get the molecular ion peak over here 60, base peak over here 67, and molecular ion peak over here at 96. So this is a typical fragmentation for the cycloalkanes. So we are not going to break the molecules in a random way, but we will follow the typical pattern for the each and every kind of functional groups. So friends, you can see here these are some functional groups. So let's go for some different types of functional groups. Next is alkene. Now friends, if we look at the alkenes, they have intense molecular ion peak. Ask me why? Because they contains a pi bond and pi electrons can be easily removed by electron bombardment, and they can easily form a intense molecular ion peak before any kind of fragmentation. So alkenes will definitely show us intense molecular ion peak. For example, in one pentene we have molecular ion peak at 70, and you can see the molecular distinct molecular ion peak in the mass spectrum. The large fragment 42 in the spectrum of one pentene, okay, this 42 is formed by the loss of ethylene molecule, okay, ethene molecule or ethylene molecule, that is a minus 28, okay. Friends, ethene is a CH2 double bond CH2, and you know that 12 plus 12 24, 25, 26, 27, and 28. So this molecule have the molecular mass of 28. So if we subtract 70 and 28, we get 42. So this 42 peak is formed by the loss of ethene molecule, and you know that this is due to the McLafferty rearrangement by the abstraction of gamma hydrogen. So this is alpha, beta, and gamma. So this is alpha, beta, and gamma. So this hydrogen from gamma carbon will be shifted over here. This will be over here, and we will get the loss of this CH2 and CH2. The final fragment formed will look like what we seen in the McLafferty rearrangement. So final molecule will look like this. So friends, if you calculate the molecular mass of this molecule, then there are four carbons, four four carbons, sorry, three carbons, C3, 1, 2, 3, 4, 5, 6, and 6 hydrogen. So it will correspond to 36 for the 3 carbon and 6 hydrogens. So it will become a 42. This fragmentation will show us base peak at 42. As it is a base peak, so this is the most abundant and stable fragmentation from the molecule. So friends, if we don't have gamma hydrogen, then you can see here in the second examples we don't have any kind of gamma hydrogen. So if we don't have gamma hydrogen, then alpha cleavage and beta cleavage is most convenient and common fragmentation pattern. So in this 2 pentene you can see that the peak at 55 is formed by the loss of methyl radical. So this methyl radical is formed and lost, and we get the peak at 55. So alpha and beta cleavage is also common in the alkene. Besides this, allylic cleavage is another important cleavage in the alkenes. So allylic cleavage we have seen over here. This is the allylic carbon, and this CH3 is lost due to the allylic cleavage. So in this we have McLafferty rearrangement, alpha cleavage, beta cleavage, and allylic cleavage. So friends, alkene have multiple fragmentation patterns. You need to remember this. Now let's go for the next group or functional group. So our next functional group is alkyne. Alkynes and alkenes have similar fragmentation pattern, but friends, you can see here we have two double bonds, so we get a very intense molecular ion peak for the molecular ion peak, because we have two double bonds and four pi electrons. So the fragmentation pattern is similar with the alkenes. And now we can see here the mass spectrum of one pentine, the molecule over here. The important fragmentation is a loss of ethyl radical via alpha cleavage to produce the propyl ion. So friends, this is the alpha cleavage. Okay, over here, and then we can see there is a formation of propyl radical. That is a it will correspond to molecular ion 39. Okay, so this is a propyl 39 over here. So this is a fragmentation pattern for the alkynes. You can see here. I will show you how the 39 is formed. So this is a actual propyl radical cation, and you can see here 12 plus 12 24, 12 plus 12 4 24, and then this is a 36, 37, 38, and 39. So we get 39 for the propyl radical cation. This is the typical fragmentation pattern for the alkynes. Okay, friends. So there are another patterns which give us the peak at 53. That is the alpha cleavage, and this will help us to get the peak at 53. So most important is its molecular ion peak. You can see here molecular mass 68, and we get the molecular ion peak at 68. It is intense due to the presence of two double bonds. Now let's go for the another functional group. So this is another functional group which is commonly observed in organic chemistry, that is the aromatic compounds, especially the benzene ring. Okay, so as you know that benzene ring also contains three double bonds. Molecular ion is very intense in case of benzene ring, but as you know that benzene doesn't come alone. It will always carry the substitution, and if we have a side chain or long side chain like CH2 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 CH3, so typical fragmentation pattern is formation of benzyl cation. Now, in case of toluene, the loss of hydrogen will generate the benzyl cation, that is a pH and CH2. This will account for the peak at 92. So this 92 belongs to the peak for the benzyl cation. Then loss of one hydrogen will make this molecule a tropylium ion. 1, 2, 3, 4, 5, 6, 7. And you know that tropylium ion, after loss of one hydrogen, it will show us at 91. So any aromatic ring with the side chain will show us the peak at 91, and this 91 will correspond to nothing but the tropylium ion. Okay, so this is how the aromatic compounds will show us the fragmentation. Now let's go for the next functional group. This is the alcohols. You know, most of the time people think that alcohol will lose the water molecule, friends, but this is not the most intense peak from the alcohol. Of course there is a loss of water molecule, that is a loss of 18 units. Okay, but this is not the intense. So what is the most intense fragment of any alcoholic functional group? There is a loss of alkyl group via alpha cleavage. So friends, you know that we have radical cation over here, but this is not stable and we get very weak molecular ion peak as it forms, and it will now break via this alpha cleavage, and we get the peak of CH2, that is this CH2 and OH at 31. Okay, this is our most convenient peak from the alcohols. Okay, this is the most convincing peak from the alcohols. We get the fragment loss of alkyl fragment, and then we get the peak at 31 due to CH2 double bond OH plus. Okay, so this is how the alcohols are usually fragment. Okay, this 70 peak is your favorite. This is loss of water molecule, that is 88 minus 18 of water molecule, we get 77, and further beta cleavage will give us peak at 55 and 42. So this 42 again belong to the alkyl chain, as the side chain carries, positive charge, it will show us the peak at 42. Okay, now I have another example in alcohols. You can see here. Now friends, tell me, we have molecular ion peak at 88, and let's see how this other peaks are formed. Okay, so if we have radical cation over here, it will transfer over here, and we get the loss of side chain. Okay, we get the loss of side chain. So we get the molecule like this, double bond OH and then plus. So friends, you can see here we have 1, 2, 3 carbons, one oxygen, that means C3. H, how many H? 1. Here there is one H. Okay, 2, 3, 4, 5, 6, 7, and then one oxygen. So what will be the molecular weight of this fragment? 36 plus 7 plus 16. It is nothing but 9, and then 5, 59. So this 59 intense peak is again formed due to the loss of alkyl group. Okay, so this is how the alcohols are fragmented in mass spectroscopy. Understood? Now let's go for the next and very common functional groups like alcohol, that is a phenol. Actually, phenol is a functional group as only one addition to the aromatic ring, that is a presence of OH group. Of course, group is this functional group will follow the fragmentation pattern of aromatic compounds. That is, this will show us intense peak because there is no other fragmentation, and loss of one electron form or double bond will give us the intense molecular ion peak. Okay, friends. So this is how we are going to see the fragmentation pattern of phenols. So you can see here we have this compound which contains one methyl group, and here the 108 peak will belong to the fragmentation of tropylium ion containing our OH group. That means 108 for our molecular ion, and then 107 for the tropylium ion containing OH groups. So friends, this is how we are completing our this part. In the next lecture, we will cover more examples or more functional groups from the mass spectroscopy. So thank you very much. And if you guys have any doubt, feel free to ask me. Thank you.